In the name of Almighty God, I'm Master Sankocha, and today I want to talk about phase transformation strains. We consider two types of strains that appear during a thermal transient involving metallurgical phase transformations. These strains originate from thermal expansion transformation induced plasticity. Other inelastic strains may also be present during a thermal transient, such as the plastic strains or creep strains. Now I want to go through the thermal expansion. It is well known that different metallurgical phases occupy different volumes at a given temperature. For example, when austenite transforms into martensite, the thermal contraction due to cooling is accompanied by a volumetric expansion when the martensite begins to form. There are two formulations for computing thermal strains in the compound material. The strain-based formulation uses a phase fraction weighted sum of the thermal strains of each phase. The density-based formulation uses the change in the density during temperature change and phase transformation. Now I'm about to go to the strain-based formulation. In the strain-based formulation, the thermal strain of the compound material is given by epsilon T. H is equal to sigma, the lower boundary I is equal to 1, the upper boundary is n, zeta to the power of I, epsilon T H to the power of I. In this equation, the thermal strains of the individual phases are computed using a scant thermal expansion model requiring a coefficient of thermal expansion and a strain volume reference temperature for each phase. Consider the simple case where phase 1 transforms into 2. In one dimension, the thermal strain is as below, where alpha T and T temperature reference are the scant coefficient of thermal expansion and strain volume reference temperature for the respective phases I. 1 and 2, figure 3-8 shows the thermal strain. For simplicity, the coefficients of thermal expansion for the two phases in the figure are constant but different. In the figure, a fictitious phase transformation has been used to illustrate when phase 1 transforms completely into phase 2 as the temperature is lower. No separate volumetric term is required to model this type of phase transformation strain, as it is included in the definition of the thermal expansion itself. Figure 3-8 illustrates the strain-based formulation for the thermal strains. Now I want to go through the density-based formulation instead of expansion thermal strain contributions from each phase separately. This formulation uses the temperature-dependent densities and the evolving phase composition to express a volumetric strain. To compute its reference density, the initial phase composition and the densities evaluated at their respective volume reference temperature are used. The evolving thermal volumetric strain is then given by this formulation. Consider, as in the previous section, a case of two phases where one transforms into the other. The temperature decreases. Initially, this fictitious material consists entirely of phase 1. The volume reference temperature for phase 1 is equal to the initial temperature, so that the thermal strain is zero at this temperature. As the temperature decreases, the density of the compound material is exactly equal to the evolving density of phase 1. As the phase transformation takes place, the compound material density changes both with temperature and the changing phase composition. Finally, phase 1 has transformed fully into phase 2, and the compound material density becomes identical to the density of phase 2 on the further reduction in temperature. See figure 3-9. For the density-based formulation, 2 points should be made. The choice of volume reference temperature for a given phase I is unsequential if the zeta 0 to the power of I is equal to 0. If different volume reference temperatures are specified for phases that are present initially, unexpected volumetric strains can result. Figure 3-9 illustrates the density-based formulation for thermal strains. Now I want to go through the transformation-induced plasticity. Plastic strains in metal result from the deviatory stresses that exceed the yield strength of the material. However, during phase transformations, inelastic strains may appear already at smaller stress levels. This transformation-induced plasticity (TRIP) is therefore different from classical plasticity in that it doesn't involve a yield criterion and that it appears at a stress level that would otherwise be insufficient to cause plastic straining even in the softest of the phases. A description of TRIP strain rate common in the literature. See, for example, reference 4, and the formulation is such that where the strain rate is proportional to the deviatory part of the second Piola-Kirchhoff stress tensor S through the transformation-induced plasticity parameter chi s to the power of TRIP tends to the D. The derivative of the saturation function phi zeta to the power of d and the rate of formulation of the destination phase zeta to the power of d values for the transformation induced plasticity parameter ca s tends to t to the power of trip will depend on the type of the phase transformation. It can depend, for example, carbon content and temperature. See reference 5 and in reference 6. The transformation induced plasticity parameter for a given steel is expressed in terms of the relative volumetric thermal strain between the source and destination phases and the yield stress of the source phase. The strain term, the expression above, is the actual thermal strain difference between the source and destination phases in terms of the temperature-dependent densities of the source and destination phases. This can be expressed as follows, which gives the ca s tends to the d and to the power of trip is equal to 2 divided by 3 multiplied by sigma ys to the power of s multiplied by rho to the power of s divided by rho to the power of d minus 1. Another method to represent the thermal strain difference is to utilize coefficients of the thermal expansion and volume reference temperatures of source and destination phases. This gives the alternative expression for the thermal strain difference because the coefficient of thermal expansion for source and destination phases case can in general be anisotropic. We use the average value of the normal components. This gives the following expression for the transformation-induced plasticity parameter. Similar propositions exist for the saturation functions table 3-1 and reference 10. Through the user-defined option, you can define the derivative of saturation function. Table 3-1 illustrates saturation functions for the trip strain rate. Type is Abrasart and expression is such that we have also other sort of type. The total TRIP strain rate is given by this formulation. Now I want to go through this total strain contribution. When the thermal and TRIP strain are computed, they can be used in solid mechanics surfaces as an elastic strain contribution. The contributions from the thermal and TRIP strains are added to form a total strain contribution in the solid mechanics interfaces. This contribution is used additively in the case of an additive strain definition or used to form in an elastic deformation gradient contribution in the case of geometric nonlinearity with nonlinear strains. See in elastic strain contributions. In the latter case, the contribution is used multiplicatively. Now I want to go to the phase transformation latent heat. The heat rate Q0 that is released during a phase transformation is characterized by the enthalpy per unit volume delta H. S tends to go to the D. See the reference 5. The heat rate that is associated with the transformation of a source phase into a destination phase can be expressed as Q0 is equal to delta on enthalpy S tends to the zeta to the power of d. The heat rates that result from each phase transformation are added, and they can be used as a heat source when solving the heat equation. A weak contribution is added to the weak form of the heat equation, where Q0 is the sum of the contributions Q0 from each phase transformations equation 3-38, and T is the temperature degree of freedom used in the heat transfer in solids interface. Now I want to go through the carburization. Carburization is a heat treatment process when component is placed in a carbon-rich atmosphere at an elevated temperature. During the process, carbon diffuses into the surface of the component, and the carbon concentration in the component changes with time as carbon continues to diffuse to the interior. The process of carburization is modeled using Fick's second law of diffusion. The carbon concentration C during carburization depends on position and time, as C is equal to Cxt, where x denotes material coordinates and T is the time. The carbon concentration represents the mass fraction of carbon, and it is thus dimensionless. The carbon concentration is governed by the following equation: the derivative of concentration based on the time plus delta minus d. Delta C is equal to 0, where d is the diffusion coefficient or diffusivity. The diffusivity can be specified directly, or it can be modeled using an Arrhenius expression of the form as follow, where d0 is a pre-exponential factor, q is an activation energy, and r is the gas constant. Now I want to go to the carbon potential model. During carbonization, the carbon-rich atmosphere can be changed over time to produce desired carbon profile near the surface of the component. In Thomson multiphysics, you can specify the carbon potential, C potential of the surrounding atmosphere as a function of time, or you can use a boost diffuse cycle, figure 3-10. For the boost diffuse cycle, the carbon potential is defined by this formulation. Now I want to go to the figure 3-10, which represents the boost diffuse cycles. Boundary conditions section: when a component is subjected to an environment of different carbon concentration, carbon can diffuse into or out from its surface. This mass transfer can be modeled in two ways. The first one is prescribed camouflux. A Newman condition carbon mass transfer is modeled using convection boundary condition. A prescribed carbon concentration in Dirichlet condition carbon mass transfer is enabled by means of a prescribed value on the surface. Special case of prescribed carbon flux is a case of zero carbon flux. Prescribed carbon flux, the convective mass transfer of carbon from the environment into a surface with outward normal n, is given by this formulation, which where B is the mass transfer coefficient and CaC is the carbon concentration of the exterior. Natural way to define the carbon concentration of the exterior is to take it as equal to the carbon potential C potential of the surrounding carbonizing atmosphere. The mass transfer coefficient can be specified directly or defined as thermal activated, such as follow, where B0 is a pre-exponential factor and QB is an activation energy. In a given situation, these quantities would have to be estimated or measured experimentally. Now I want to go through the prescribed carbon concentration. A simple way to model the carbon exchange is to simply prescribe the carbon concentration at the surface of the component to be equal to the carbon concentration of the exterior. This modeling approach avoids having to characterize the carbon mass transfer, but it may instead exaggerate it because the surface will be saturated. I read a literature for you, which was written by Leblon de Barks, and the name is a new kinetic model for thermal metallurgical phase transformation in series, including effect of austenite grade size. The next one, Koistinen and Marburger, and the name is general equation prescribing the extent of the Austenite and Martensit transformation in pure iron carbon alloys and plain carbon steels. The next is Denis Guattari, and the name is stress phase transformation interactions, basic principle modeling and calculation of internal stresses. The next was written by DeVaux, and the name is mathematical models of unstable phase transformation is still and predicted plastic behavior. The next was written by Lissig and was the name was quenching theory and technology. The next was written by DeVaux and the name mathematical modeling of transformation plasticity in steel. The next was written by Leblon and the name is Mathematical Modeling of Transformation Plasticity in Steel 2, Coupling with Strain Hardening Phenomena. The next was written by Guy Celerius and the name is Numerical Simulation of Stress due to Solid State Transformations, the simulation of laser hardening, doctoral dissertation. The next was written by Guy Hellstern, and the name is Modeling and Characterization of Martensit Formation in Low Alloyed Carbon Steels. The next one was written by a Butcher, and the name is Comprehensive Model of Thermoelastoplasticity with Phase Transitions Steel. The next was written by Kukali and Bonkopolan, and the name is phase transformations in various alloys. The next one is written by Mekishore and the name is Computational Model for the Prediction of Steel Hardenability. The next one is written by Oldenburg and the next name is Austenite Decomposition during press hardening of boron steel computer simulation and test. The next was written by Andrews and the name is Empirical Formulate for the calculation of some transformation temperatures. The next was written by Stephen and Hines, and the name is Temperature Formation of Mountain Seed and buying it in Lala is still. The next one was written by Manier and John Mann, and the name is Hardenability Concepts with Applications to Steel. The next was written by A.S. Steam Standard, and the name is Standard Hardness Conversion Tables for a Metals Relationship Among Brine Hardness. The next was written by Hitchen, and the name is Modeling Kinetics of Phase Transformation for the Indirect Hot stamping process to focus on car body parts with Taylor properties. The next one was written by Haltgren, and the name is Discussion über the physics hardenability, and the next one was written by Odie and MacDill and Carson, and the name is Microstructural Predictions, including arbitrary thermal histories, re-austenization, and carbon segregation effect. Thank you so much for watching my tutorial video until the end. And today is 28th of May 2026. Time is 7:03 p.m. Also, you can download the appropriate and related console simulation file from my github.com/masterscript.